Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the course Analysis of Variance and Design of Experiments. So, you can recall what we have done up to now. Our basic objective is to develop a test for the null hypothesis, where we want to test the equality of more than two parameters. And we had discussed earlier that these tests can be obtained either by using the likelihood ratio test methodology or using the principle of least square also. And we had discussed that we will try to do both the methodologies here, and then I will try to show you that how they are interrelated, and after that, once you are convinced that both the methodologies are going to give you the same outcome, then you can use any one of them in the later part. So, now up to now what are we doing? We have discussed first that how are we going to estimate the parameters in the linear model. So, we had two parameters, means a beta vector and sigma square. Remember one thing, when I say two parameters, that means one here is vector beta and another here is a scalar sigma square. And in case if you try to see the total number of parameters, there will be beta 1, beta 2, beta p and sigma square, right. So, there will be p plus 1 parameters, and if you are trying to include the intercept term also, and if you are trying to consider the model with the parameters beta 0, beta 1, beta 2, beta p and sigma square, then the number of parameters are going to be p plus 1, that is p plus 2 parameter. So, that will be our understanding, that depending on the situation we will try to consider it accordingly. There should not be any confusion with this part, right. So, now we have learned how we can obtain the least squares and maximum likelihood estimator of these parameters, which are involved in the linear model. Now, we have to use it, and for that we also have discussed different types of theorems and results, which are going to help us for the development of a test of hypothesis. So, now from this lecture we are going to develop the likelihood ratio test for a null hypothesis, where we are trying to test more than two parameters related to the regression coefficients, or beta 1, beta 2, beta p. Now, remember one thing, that whenever we are going to talk about the test of hypothesis for the equality of more than two parameters, we are talking of the parameters that are involved in the vector beta and not sigma square. For sigma square, we will try to develop a different type of test of hypothesis depending on the condition. Well, I am sure that you already have done it in your statistical inference, where you try to test the hypothesis sigma square equal to sigma naught square or sigma 1 square equal to sigma 2 square in one or two sample tests. So, those things we will consider later, but at this moment we are going to consider only the test of hypothesis that are related to the parameters beta 1, beta 2, beta p. So, now in this lecture we are going to develop the likelihood ratio test for such a hypothesis. Once we develop this thing, after that I will take two more cases where I will try to develop the test of hypothesis for the linear parametric function and for a set of linear parametric function. So, now in this lecture I am going to give you the detailed steps that how one can develop the test of hypothesis and how we can develop or find the distribution of the test statistic. And in this lecture I am going to use all the results which I have developed so far. So, this is very important for you that before going into this lecture, you must have a quick revision of all the results that we have done up to now, at least in the last couple of lectures related to the linear models. And here I will simply ask you or refer you to those lectures, and I will try to show you that how those results are going to be applied here, right. So, let us begin our lecture. So, now we are going to discuss the development of the test of hypothesis concerning the parameters of a linear model or a linear regression model, right. And these tests of hypothesis will be used later on in the development of tests based on the analysis of variance. Now, the first question comes here, what is analysis of variance? So, if you remember in the earlier lectures I had discussed what is analysis of variance and why are we going to do it. So, in that technique of analysis of variance, we try to partition or break down the total variation involved in the variable y, that is your response variable, into different orthogonal components. And each of this orthogonal component is going to represent the variation due to a particular factor contributing in the total variation, right. So, suppose if I say that the total variation is divided into 3 components, say Q1, Q2, Q3, right. So, that will be something like Q1 plus Q2 plus Q3, and this Q1, Q2, Q3, they are going to be orthogonal components, and each of this Q1, Q2 or Q3 that is going to represent a particular type of variation due to a particular type of factor that is affecting the outcome. And then we will try to see that which factors are important or not. So, we are going to consider here the linear model. Just for the sake of quick review, I will just explain you here once again, so that we are once again comfortable with the symbols and notation in this lecture. So, let y1, y2, yn be independently distributed random variables following a normal distribution with mean expected value of yi is equal to j goes from 1 to p summation beta j x I j and variance sigma square. And in case if I try to represent all this y1, y2, yn in the form of a random vector y like this, then y is going to be n cross 1 column vector, and this expression which I have written here for representing the form of yi, that can be written in the form of a linear model or a linear regression model y equal to x beta plus epsilon. And I already have discussed this development, that how these this linear model is obtained, right. So, I am not going to explain here again, but I believe that you know it. So, here in this case x is going to be n cross p matrix of p covariates x1, x2, xp, and on each of the variable we have obtained a number of observation. Beta is here a p cross 1 vector of the regression parameters that is unknown, and epsilon is a n cross 1 vector of random error component or disturbances, and with expected value epsilon equal to 0, and covariance matrix of epsilon is sigma square I, and we assume that epsilon follows a normal distribution, right. So, we can write down here that expected value of y is equal to x beta, covariance matrix of y is given by here sigma square I. So, that we already have done, right. And you can see here that we are trying to assume here that epsilon follows a normal distribution right from the beginning. Why? Because we are going to use the likelihood ratio test, and in likelihood ratio test you know that you need to assume the distribution. And in case if you try to consider the least square estimation, then you will see how we are going to introduce these assumptions. So, now we consider the development of likelihood ratio test for the null hypothesis related to the analysis of variance. And remember one thing, whatever I am going to develop here using the theory of likelihood ratio test, I will try to find out the same thing, same test once again on the basis of least square principle also at a later stage. And I said, and as I said earlier, my idea here is that I am trying to find the same thing from two different approaches, so that I want to, or I can demonstrate that the test used in the analysis of variance can be derived using the least square principle as well as the likelihood ratio test, so that you are more comfortable in the future whenever you have to develop a new test of hypothesis under a new type of conditions. Okay. So, now we consider here a test of hypothesis like this one, say H naught beta is equal to naught. So, if you try to now see here, what is here beta? Beta here is a vector quantity, like beta 1, say here beta 2 and here beta p, right. Means at this moment I am not introducing the concept of intercept term here, but we are using simply beta 1, beta 2, beta p to indicate any of the parameter in the linear model. So, what we want to test here? We want to test here the null hypothesis that H naught beta 1 is equal to beta 1 naught, beta 2 is equal to beta 2 naught, and beta p is equal to beta p naught. That means, I want to test here a hypothesis beta equal to here beta naught 1 like this, beta naught 2 like this, beta naught p, and this I am going to denote here as by here beta naught. So, this is a here a vector, this is here a vector. So, this is what we want. So, we want that the equality of all the p parameters at the same time, right. So, we consider here the null hypothesis H naught beta is equal to beta naught, and remember one thing, beta naught I am writing here in the superscript, right. So, this and both beta and beta naught, they are p cross 1 vector, and this beta naughts vector or all the values inside this vector beta 1 naught, beta 2 naught, beta p naught, they are known, and sigma square is unknown, right. So, now definitely we are going to develop a test of hypothesis for beta, and betas are unknown. So, we need to estimate it. So, now either you employ the principle of maximum likelihood or the least square. You know that this maximum likelihood estimator or the ordinary least square estimator, they are going to give us the best linear unbiased estimator. That means, they are going to have the minimum variance in the class of linear and unbiased estimator, and when the betas are estimable, for that we have learned the condition that rank of x equal to p, that is the full column rank matrix of x. So, we assume simply here that all beta i's are estimable. Now, we try to develop the likelihood ratio test, right. Now, you know, when you want to develop the likelihood ratio test, there are a couple of steps. The first step is that you have to specify the parametric space. The parametric space is going to be defined under H naught and under the whole parametric space, and then you have to write down the likelihood function. So, since you are assuming here a normal distribution, so you know how to write down the likelihood function, and then you need to maximize the likelihood functions under the sample space and under the whole parametric space. And then you have to take its ratio, and then whatever the ratio come, that you need to simplify, so that you can find out the probability distribution of the likelihood ratio test statistic. So, these are the steps that we are now going to follow in this lecture one by one. So, I will try to go through quite slowly, and I will try to explain you all the steps. You please try to follow with me, right. Okay. So, now if you try to see here, first I try to define here the parametric space capital omega, right. So, now if you try to see how many parameters are going to be there in this parametric space, they are beta 1, beta 2, beta p and sigma square. So, there are altogether p plus 1 parameter. So, this parametric space indicated by capital omega is going to be a p plus 1 cross 1 dimensional space, and this is a collection of points related to beta and sigma square, such that beta I lies between minus infinity and plus infinity, and sigma square is greater than 0 for all I goes from 1 to p, right. And now, when I say under H naught, you are assuming that beta is equal to beta naught. That means all betas are known, and we are indicating that known value by beta naught. Then in that case, what will happen to this capital omega? Out of this beta 1, beta 2, beta p, this beta 1, beta 2, beta p, now they are known. So, the only parameter that is left to be unknown is sigma square, right. So, in case when H naught beta equal to beta naught is true, then the sample space becomes only a one dimensional space, which is indicated by small omega, and this is a collection of the points of all known values of the beta i's indicated by beta naught vector and a known sigma square. So, now in this case sigma square will be greater than 0. So, that is my sample space. Now, in case if you try to see, because you have assumed the normal distribution, so you can write down here the likelihood function of y1, y2, yn that we already have actually done, and we try to derive the maximum likelihood estimates of the parameters. So, you can see here, this is here the likelihood function n upon 2 pi sigma square raised to the power of n by 2 exponential of minus 1 upon 2 sigma square y minus x beta naught transpose into y minus x beta naught. So, you can see here that in this case I have replaced here beta by beta naught, and in case if you try to write down under the capital omega, then this beta naught will remain as beta, right. So, now first I try to find out here the maximum value of likelihood function under capital omega. That is the first step in the likelihood ratio test statistics. So, if you try to see here this I am writing here the likelihood function, and then I am trying to find out its maximum value over the whole parametric space omega. Now, you have to just think and tell me that what are the values of beta and sigma square for which this likelihood function is going to be maximized. Now, if you try to recall how you had found the maximum likelihood estimators of beta and sigma square, the basic principle which is involved in finding the maximum likelihood estimators is the values of the parameters which are going to maximize the likelihood function. So, that means do not you think that instead of doing the entire algebra once again, if I simply say that the values of the maximum likelihood estimators of the respective parameters are going to provide us the maximum value of the likelihood function. That means, in case if I say in the simple words, you have here a likelihood function which is a function of beta and sigma square, and if you simply replace the values of beta and sigma square in the likelihood function by their maximum likelihood estimators, then the value of likelihood function will become automatically maximum, right. So, now instead of doing this algebra, we try to simply use the maximum likelihood estimators directly, and that was the reason I had given you all the results directly earlier, right. So, now if you try to see the likelihood function is maximum over omega when beta and sigma square are substituted with their maximum likelihood estimators, and we already have found that the maximum likelihood estimator here is x transpose x whole inverse x transpose y, and which is indicated by here beta hat, and the maximum likelihood estimator of sigma square here is 1 upon n y minus x beta hat transpose into y minus x beta hat, and this is indicated by here sigma square hat. Now, one word of caution. Now, from this lecture we have formally started the development of test statistics for such a hypothesis. And up to now we were trying to discuss different types of concepts related to maximum likelihood estimator, ordinary least square estimator. So, when I am trying to discuss those things in the same lecture, I had used different symbols and notation. For example, earlier if you remember, I had used the symbol beta hat for ordinary least square estimator or the least square estimator of beta, and beta tilde for the maximum likelihood estimator of beta, and same was true was sigma square hat and sigma square tilde, right. They were the least square and maximum likelihood estimator of sigma square, right. So, now we are just going to work only with the maximum likelihood estimator. So, now I am using here the symbols and notation beta hat and sigma square hat to indicate the maximum likelihood estimators, right, because earlier since I was trying to explain both the estimator in the same lecture. So, I had to take different symbols and different notations, right. So, that you have to be careful, but it is not a very big deal. Okay, so, now what I try to do here, I try to write down here the likelihood function, and you can see here I am simply trying to replace here beta by beta hat and sigma square by sigma square hat. You can see here that is sigma square hat, right. You can see here. So, I am just substituting these values over here. Now, in case if you try to observe here one thing here, that when you are trying to write down here this quantity minus 1 upon 2 sigma square hat, and here you have y minus x beta hat transpose y minus x beta hat, and if you try to see here this structure of sigma square hat. So, when you are trying to replace here the value of sigma square hat to be here 1 upon n y minus x beta hat transpose y minus x beta hat, then this is a scalar quantity in the numerator of this sigma square hat. This is going to be cancelled by this quantity y minus x beta hat transpose y minus x beta hat. So, now you will get here only exponent of minus n by 2, and yeah, means here in this case you have simply substituted the value of sigma square hat. So, you can see here finding out this expression is not difficult, and this is going to give you the maximum value of the likelihood function over the whole parametric space. You can see here the algebra is very simple, but the conceptual part is more important, which you have to understand. Now, the same thing I can do when I try to find out the maximum value of the likelihood function under H naught. So, now under H naught you have seen that beta is known as beta naught. The only parameter which is unknown, that is sigma square. So, in case if you try to look at the structure of this sigma square hat, you are trying to replace here this beta hat by beta naught, and this will give you here the estimator of sigma square hat like this 1 upon n y minus x beta naught transpose y minus x beta naught, because under H naught beta equal to beta naught is known to us. And now, in case if you simply replace beta by beta naught and sigma square by say here sigma square hat in the likelihood function under H naught, we can obtain the likelihood function here as like this, 1 upon 2 pi sigma square hat raised to the power of n by 2 exponential of minus 1 upon 2 sigma square hat y minus x beta naught transpose into y minus x beta naught. And now, if you try to see here that once you try to replace here the value of this sigma square hat here, and if you try to observe the structure of this sigma square hat under H naught from this expression, you can simply see that this numerator part y minus x beta naught transpose into y minus x beta naught, that is getting cancel out, and you will get here only here exponential of minus n by 2. And the first factor you simply try to replace here sigma square hat. So, you get here this expression. And now, when you are trying to replace the value of sigma square by its maximum likelihood estimator, then definitely this is going to provide us the maximum value of the likelihood function under small omega, that is under H naught, that is under the sample space. So, now you have completed the first part of the likelihood ratio test, that you have obtained the maximum value of the likelihood function under the whole parametric space and under the sample space. Now, what we have to do, the second step is we need to find out the likelihood ratio test statistic. So, we know from the theory of statistical inference that the likelihood ratio test statistics is given by, say here, the maximum value of likelihood function under the small omega divided by the maximum likelihood of maximum value of the likelihood function under capital omega, right. And this is usually indicated by the symbol lambda, small lambda. Now, you have obtained these expressions earlier in the numerator and denominator. You simply try to substitute them here. So, you can see here that the quantity was coming out to be 1 upon 2 pi to the power of here n by 2, and then 1 over sigma square hat, right. And then you had here exponential of here, say here minus n by 2, and then here n by 2. So, now what you have done, that you are simply trying to replace this sigma square by their respective estimator under capital omega and under small omega. And when you are trying to take the ratio, this part exponential of minus n by 2 will get cancel out from the numerator and denominator. So, you are getting only here the quantity, this one y minus x beta hat transpose into y minus x beta hat divided by y minus x beta naught transpose y minus x beta naught, that is the power of n by 2, right. So, now I have to simplify it. The reason why I want to simplify is very simple, that I want to find out the distribution of lambda, that is the probability distribution of lambda. And in order to find out the probability distribution of lambda, you can see here that we have the quantities in the numerator and denominator of lambda, which are in the form of quadratic forms. And for the results that we have done related to the quadratic forms, we have considered the quadratic forms like y transpose A1y and y transpose A2y, right. And we have obtained different types of relationship between them. So, my objective is very simple. I want to simplify the quadratic forms in the numerator and denominator in such a way that it is helpful for me in finding out the probability distribution of lambda, right. So, what I try to do here, that I try to consider here the quantity in the denominator, and I try to do here one thing, I try to add and subtract here x beta hat. In both the factors, right. And then I try to write down here y minus x beta hat plus x beta hat minus x beta naught in both the factors here. Now, if you try to see what I am trying to do here, why I am trying to add and subtract x beta hat, because if you try to see, I am trying to match y minus x beta hat in the denominator with the y minus x beta hat in the numerator. And the reason for this, that will be clear to you as soon as we try to move in further slides, right. So, now after this I simply try to expand it and I try to invert it, means the denominator will go into the numerator and this numerator will come in the denominator, and I express it by here minus n by 2. And in case if you try to see here this part is simply, if you try to take here outside this common x, this will become here beta hat minus beta naught, right. So, if you simply try to open it here, you will get here two terms. One term will be y minus x beta hat into y minus x beta hat transpose and plus x beta hat minus x beta naught transpose into x beta hat minus x beta naught, and the cross product term that will become 0, that you can verify very easily, very simple algebra. And then if you try to invert it, you will get here the quantity like 1 plus beta hat minus beta naught transpose x into beta hat minus beta naught divided by y minus x beta hat transpose y minus x beta hat, right. Because you can see here that this factor is going to be the common into the numerator and denominator, this factor and this factor, and they will give rise to the factor here 1, right. And then I try to just express here this quantity in the numerator as q1 and the quantity in the denominator here as a q2, which I have written here. q1 and q2, they are going to be like this. And observe one thing, I have used here a symbol, a small q1 and a small q2. Later on I will use one more symbol, capital Q1 and capital Q2, which are going to define like a random variable corresponding to the values small q1 and small q2, right. Now, I try to simplify this q1 and q2, and my objective is very simple. I want to express them in a form so that I can find out their probability distribution. So, now at this moment I would request you simply ignore whatever we have done up to now and simply try to concentrate on the simplification of q1 just as a mathematical problem, right. So, in case if you try to see how I am going to do it here, suppose I am considering here q1, which is beta hat minus beta naught transpose x into beta hat minus beta naught. So, now I try to replace here the value of beta hat. So, this becomes here x transpose x whole inverse x transpose y minus beta naught, and then this transpose, and the remaining part will have the same operation, right. I try to replace here beta hat by its expression and beta naught will remain as such. Now, in case if you try to take here common from this expression like this x transpose x whole inverse x transpose, then this can be written here, say here y minus x beta naught like this, and the same operation I am trying to do here also. Now, after that you simply try to simplify it. So, this will become here, you can see here this is here transpose, right. So, this will become here y minus x beta naught transpose into x transpose x whole inverse. This x transpose x will come here like this, and then here the quantity from the second bracket, x transpose x whole inverse x transpose y minus x beta naught. And now if you try to see here what is happening, this x transpose x into x transpose x whole inverse, that is becoming here I, identity matrix. So, I can write down here this quantity y minus x beta naught is coming here, this quantity x into x transpose x whole inverse into x, this is coming here, and then this quantity here y minus x beta naught is coming here. So, now we have simplified it. Now, I will try to explain you after I simplify the Q2 also, that why I am trying to do it. Right. Similarly, if you try to see here, I try to simplify here Q2 also. Q2 is y minus x beta hat transpose y minus x beta hat, and so I try to simply write down here this value of beta hat like this here. And then you can see here, if you try to take this y common on the left hand side and right hand side, this matrix I minus x into x transpose x whole inverse into x transpose into the same quantity. So, and this is a hat matrix which is an idempotent matrix. So, I can write down here this expression as say y transpose I minus x into x transpose x whole inverse into x transpose into y. And now, I try to do here one more manipulation, and I will try to explain you after I complete this slide. I try to rewrite here y here as say y plus minus x beta naught, right, here and here also plus minus x beta naught. And then I just try to simplify this expression. So, this will become here y minus x beta naught into this hat matrix into y minus x beta naught, which is here like this, and rest all the terms they will become simply 0, that you can verify. Because we are going to use here the result that hat matrix into x, that is I minus x into x transpose x whole inverse into x transpose into x, that is going to be x minus x x transpose x whole inverse x transpose x, which is equal to here, see this is here I, and so this becomes here x minus x, which is a null matrix. Now, the reason why I am trying to add and subtract here x beta naught, and I am trying to express this quadratic form in terms of this quadratic form. You can see here what is the difference between the two quadratic forms here. You can see here this variable here is y, and here the variable here is y minus x beta naught. And you can see here in this earlier expression of Q1, this is here y minus x beta naught. This variable is being used, and I wanted to bring the random variables involved in the quadratic forms of Q1 and Q2 to be the same. That is also why this I will try to explain you in the forthcoming slides. Right, okay. Yeah, means they are actually going to help us in finding out the probability distribution of the likelihood ratio test statistic. So, now we would like to find out the decision rule for testing H naught on the basis of the likelihood ratio test statistics lambda. So, in case if you want to take this decision, first you need to know that if lambda is a monotonic increasing or decreasing function of Q1 upon Q2 or not. Why? Because you can see here that earlier you had used here this term here. I can show you here in this red color like this one, right, and I can write down here that your lambda was here like this one, because based on that whether this is going to be a monotonic increasing or decreasing function of Q1 upon Q2, we have to take a decision rule, we have to frame a decision rule. So, I simply want to do here a small algebra to check whether this lambda is a monotonic increasing function of Q1 upon Q2 or monotonic decreasing function of Q1 upon Q2. So, let this G be equal to Q1 upon Q2 just for the sake of simplicity. So, this lambda can be expressed 1 plus G raised to the power of minus n by 2 And now if you try to differentiate lambda with respect to g, this will come out to be here like this, and you can see here from this expression that as g increases, lambda decreases. So, I can say here that lambda is a monotonic decreasing function of g, that is q1 upon q2. Well, that is a very simple algebra that you know. So, now once I know that lambda is a monotonic decreasing function of q1 and q2, so using the results of the likelihood ratio test, I can give here the decision rule as reject H naught if lambda is less than lambda naught, where lambda naught is a constant to be determined by the condition on the basis of size of the test alpha. So, we are assuming that the size of the test here is alpha, and based on that we have to find out the value of lambda naught, and lambda naught is a constant. That is a very standard rule in the likelihood ratio test. So, and in case if you are not aware or you have forgotten this thing, I would request you that pick up a book of statistical inference and try to read about the likelihood ratio test. So, that is a standard result which I have used here. Now, the question here is this: what does this actually mean? When I am trying to write down that here you are writing here reject H naught if lambda is less than or equal to lambda naught. This lambda naught is unknown to us, that we do not know. So, the first question comes here: can we simplify it so that we can find out the value of this lambda naught in terms of the function what we have? And remember one thing, what we have here? We have here the likelihood ratio test statistics lambda, which is a function of q1 upon q2. So, anyway, I would like to have a decision rule in terms of q1 upon q2. So, I simply do a very simple algebra just to simplify the condition lambda less than or equal to lambda naught. So, lambda here is coming out to be 1 plus q1 upon q2 raised to the power of minus n by 2 and less than equal to lambda naught. So, this will become here, just for the sake of simplicity I am writing this q1 upon q2 here as a g. So, this will become here 1 upon 1 plus g raised to the power of n by 2 less than equal to lambda naught, and if you try to just simplify it, it will come out to be here that g is greater than or equal to lambda naught raised to the power of minus 2 by n minus 1. So, you can see here you are saying that lambda 0 is a constant, right, and n is also known to us, right. So, do not you think that this entire quantity is also a constant? So, I simply try to indicate by here a constant c, and I can simply write here my rule here as a g is greater than or equal to c, and g here is q1 upon q2 is greater than or equal to c, right. So, and what is here c? This is a constant to be determined by the size alpha condition of the test. So, now the same rule which you have written here that reject H naught if lambda is less than or equal to lambda naught, that I can write down reject H naught whenever q1 upon q2 is greater than or equal to the constant c, where the constant c is going to be determined by the size alpha condition of the test, right. Now, the question here is that how to find out the this here c, but before that I would just like to give you an idea here so that you are comfortable and you can understand that as we discussed in the beginning, that the relationship between or the utility of understanding least square principle and maximum likelihood principle for obtaining the test statistics. So, here at this moment I would simply like to inform you here that you can see here now this entire test is depending on the value of q1 upon q2, and remember one thing, that q1 upon q2 is being obtained from the likelihood ratio test. Now, the same statistics q1 upon q2 can also be obtained by the least square method, but we are going to talk about at later stage, right. And the test statistic what we are going to obtain through this likelihood ratio test statistics and this least square principle, they are going to be the same, right. And This is simply based on the ratio Q1 upon Q2 actually. So, now we need to find out the distribution of Q1 upon Q2, so that I can find out the value of here this constant C, because you see the values of small q1 and small q2, they are simply the functions of your, you can see here this observations, right. Q2 if you try to see, y is known to us, x is known to us, beta hat is known to us. So, you can compute Q2. What about Q1? Beta hat is known to us, beta naught is unknown to us, x is known to us. So, you can also compute Q1. So, this now Q1 and Q2 are known to us, only the constant C is not known to us. So, for that now we try to use the earlier discussed theorem, and we try to find out their distributions, and then we use them in finding out the distribution of Q1 upon Q2. Right. So, now I try to first introduce you here with the theorem that we had done earlier, but I will try to modify it in the context of our setup. So, this I am calling here as a theorem 9, and yeah, up to earlier theorems we have done in the last lecture also. So, suppose we define here a new random variable here z as y minus x beta naught. Do you remember where we have used the quantity y minus x beta naught? Okay, try to recall. And then we try to define here two more variables here q1 and q2, and which are based on the random variable here, say here z. So, this is something like a quadratic form based on the random variable here z transpose x into x transpose x whole inverse x transpose, and another random variable q2 using the same random variable z with a different matrix, that is now a hat matrix I minus x into x transpose x whole inverse into x transpose. Now, my result is that q1 upon sigma square and q2 upon sigma square, they are independently distributed, and when h naught is true, then q1 upon sigma square follows a chi-square distribution with p degrees of freedom, and q2 upon sigma square is following a chi-square distribution with n minus p degrees of freedom. And now, you can see here there is no involvement of the non-centrality parameter, because this is a central distribution. Why this is a central distribution? Because we are trying to say that y equal to x beta plus epsilon is my model, where expected value of y is going to be here x beta, and under h naught expected value of y is going to be x beta naught. So, in case if you try to take this random variable, say y minus x beta naught, and try to take its expectation, then this is going to be 0. So, now I am trying to define here this as a expected value of z is equal to 0, and this z is defined here. So, now you can see here the chi-square distributions are based on the random variable which has got mean 0. So, the non-centrality parameter is going to be 0. Okay. So, now if you try to see, now we are going to implement this rule here, but before that let me try to show you here the proof. But now you have understood that there is nothing new, but we are just going to use the earlier result. So, under h naught, the expected value of z is going to be x beta naught minus x beta naught, which has got a mean 0, and variance of z is going to be same as the variance of y, which is sigma square I, right. So, now you can see here that z is also a linear function of y, and y follows a normal distribution. So, z will also be a normally distributed random variable, and z will follow a normal distribution with mean vector 0 and covariance matrix sigma square I. So, that means all the z1, z2, zn, they are going to be IID, and when they are trying to follow the normal distribution, they are IID. All those results which we have used in the earlier lectures, they can be used here, but now the question is which of the results? We have done a couple of results. So, now let us try to see that how are we going to prove the results. So, now first I try to prove here these three parts, that Q1 upon sigma square and Q2 upon sigma square, they are independent. So, for now you can see I have expressed Q1 and Q2 in the form of quadratic form. So, you can use here the results where the conditions for the independence of two quadratic forms are found, and then we have the results that about the distribution of the quadratic forms. So, we try to use them now here, because we know that these two matrices x into x transpose x whole inverse x transpose and this hat matrix I minus x x transpose x whole inverse into x transpose, they are idempotent. You can see here this is x into x transpose x whole inverse into x transpose. Now, you multiply by the same matrix x into x transpose whole inverse into x transpose. This is going to be here x transpose x, now x transpose x into this x transpose x whole inverse, that is going to be here I, and you can see here this will come out to be only x into x transpose x whole inverse into x transpose. So, and the idempotency of this we already have done earlier. So, both these matrices are going to be idempotent. So, what you can see here that these two matrices which are defined in the quantities or the variable Q1 and Q2, both are idempotent matrix, right. And now, let us try to find out their trace. So, we already have found the trace of this hat matrix, trace of I minus x into x transpose x whole inverse x transpose, that was coming out to be here as a and minus p. And if you try to see what is this quantity, this is the same quantity which is the matrix here, trace of x x transpose x whole inverse into x transpose. So, we can write down here as say trace of x transpose x whole inverse into x transpose x, which is trace of identity matrix of order p, which is equal to here p, right. So, now we have found the trace of both the matrices which are present in the two quadratic forms Q1 and Q2, this and this. So, now you can use the result, the theorem 6 that we did earlier, that Q1 upon sigma square will follow a chi square distribution with the degrees of freedom, which is the trace of the involved matrix, which is here. You can see the involved matrix here is x into x transpose x whole inverse x transpose, and its trace is given by here p. So, this is going to be here chi square with p degrees of freedom. And similarly, for here Q2 upon sigma square, that is also going to follow the chi square distribution, because the involved matrix here, which is the hat matrix, that is an idempotent matrix, and a trace is given by here and minus p. So, this will follow a chi square distribution with degrees of freedom and minus p, right. And now, we have to show the independence of the two. So, I have shown you here that the result that A into B is equal to null matrix, where A here is hat matrix and B here is x into x transpose x whole inverse x transpose. If you try to multiply them, this will come out to be a null matrix. So, both this Q1 and Q2 quadratic forms, they are independent under H naught, and hence this theorem is proved, right. So, now if you try to see, before I go further, if you try to observe how this Z Q1 and Q2 have been constructed. Now, come back to the earlier slides and try to see here the forms of Q1 and Q2. So, you can see here your variable here is y minus x beta naught, and this matrix here, what is this thing? Do not you think that this is related to like Q1 quadratic form that you have considered? And similarly, if you try to go for here Q2, you can see here this is the same form that you have expressed here as say capital Q2, but the only difference here is that in this Q1 you are trying to use here is small y, which is the values, and in Q2 also you are trying to use small y, which are the values. But now you are trying to define here capital Q1 and capital Q2, which are your actually random variables. So, it is the same theory that in statistics we always try to indicate the random variables by capital letters and their values by small letters. That is the same logic I have used here, right. So, and Z here is the same random variable which is involved with the quadratic function, right. So, now after having this result, we have seen that this Q1 and Q2, they are independently distributed. So, under H naught. Now, if you try to recall the definition that how we have defined the F distribution, that was the ratio of two chi-square random variables divided by their degrees of freedom. This used to follow a F distribution with the degrees of freedom df1 and df2, which are in the numerator and denominator. So, the same result I can use here, and I can see here that this chi1 square is something like your here q1, chi2 square is something like here q2, and both are independent. So, I can write down here q1 divided by its degrees of freedom, which is here p, and q2 divided by its degrees of freedom n minus p. This follows a central F distribution, or I can say that n minus p upon p, capital Q1 upon capital Q2 follows a F distribution, or rather a central F distribution with the degrees of freedom p and n minus p. Hence, the constancy in the likelihood ratio test statistic lambda is given by this F at level of significance 1 minus alpha with the degrees of freedom p and n minus p, where this quantity f1 minus alpha n1 n2 that indicates the upper alpha percent point on the F distribution with n1 and n2 degrees of freedom. So, now you can see here you have obtained here the value of constant also. So, now you are done. You have obtained the statistics, you have obtained its distribution, you have obtained the likelihood ratio test statistics, you have obtained the critical value. Now, what is left in the test of hypothesis? And now, I can just compile all these results in the form of a analysis of variance table, that is called as Anova Table. That is the more popular form. So, the Anova Table for testing H naught beta equal to beta naught is given by like this, that in the first row we try to write down the source of variation, degrees of freedom, sum of squares, mean squares, and F value. And then you can see here source of variation are here, because you are trying to take here the model y equal to x beta plus epsilon. So, all the independent variables they are clubbed in this term x beta along with their effect, and remaining part here is only random error, right. So, the total variation in y can be divided into two orthogonal parts, one due to x beta that we are writing here as a due to beta, and another part is due to random error, which we are calling here as a error, and their sum, and their corresponding degrees of freedom are p and n minus p, and if you try to add them here together, this will come out to be here n, right. And in case if you try to see the sum of squares that are obtained by the term q2, and if you try to sum them q1 plus q2, this will be here y minus x beta naught transpose y minus x beta naught, and this is called as total sum of squares, right. And if you try to define here the mean square, they are divided they are defined as q1 divided by degrees of freedom p and q2 divided by the degrees of freedom n minus p, and if you try to take the ratio, this will give you here the f value. Now, you can see here that here in this case this q1 plus q2 is equal to here TSS, and the degrees of freedom p plus n minus p is equal to here n, right. So, now if you try to see many times you will see in the, or you will find in the classroom teachers to tell us that out of these three sum of square due to beta error and total sum of square, try to find two sums of square and try to find the third sum of square by subtraction. Why? Because now you see you are trying to divide the total sum of squares into two parts, two sum of squares q1 and q2, and both are orthogonal. You have proved that they are independent, and this is done by Fisher-Cochran theorem, and that is why you are able to write down that the degrees of freedom of sum of squares due to beta and the sum of square due to error, they are equal to the degrees of freedom of the total sum of squares. So, now this result is valid here only when the Fisher-Cochran theorem holds true, and in order that Fisher-Cochran holds true, all the sum of these partitions Q1 and Q2, for example, in this case, that should exactly be equal to the total sum of squares, and that is why out of these three quantities, that total sum of square is equal to sum of square due to beta plus sum of square due to this error. We try to find out two quantities, we try to compute two quantities on the basis of data, and we try to find out the third quantities by using this relationship. That is the reason. So that Fisher-Cochran theorem holds true and my results are valid. So, you can see here that in this lecture we have learned that how the likelihood ratio test can be found, and you can see that whatever results we have done in the earlier lecture, they are used here directly, and I have tried my best to give you the minor details of this process, all the steps of this test of hypothesis, but it is very important for you now that you try to derive this expression, try to understand each and every reason yourself without looking into the notes. Try to find the same thing, and if you get trapped, try to look into your notes or slides or lectures and try to see whether you have understood it or not, and try to give replies to yourself that why this is happening, and this way I am sure that you will understand it very easily. So, you try to have a quick revision, you try to revise it thoroughly also, and I will see you in the next lecture. Till then, goodbye.